For our preliminary example of trying to find an area in between two curves, I'd like to consider the region bounded by y equals 12 minus x squared and y equals x squared minus 6. So first off, to consider what both of these regions look like, the second function that is listed would be your standard parabola with a vertex shifted down 6 units. So somewhere down here. And then opening in, oh boy, in an upward direction. This would be the standard parabola with the vertex shifted up 12 units and then opening in the downward direction. We'll just kind of eyeball this one. So the region in question would be the region in between these two curves. Now you'll notice that we were not given endpoints or bounds for this curve. Once again, this is y equals x squared minus 6, and this one is y equals 12 minus x squared. Now, if we were to consider one small interval within this region, we could once again draw that representative rectangle that extends all the way from the top of the function down to the bottom of the function. Now, with that in mind, the height would once again be considered a change in y. The top function is your downward opening parabola as defined by this. So that would be 12 minus x squared minus your bottom function, which is the parabola opening in the upward direction. That would be x squared minus 6. The base of this representative rectangle would be equal to simply a little tiny change in x. As far as bounds are concerned, the bounds for the region are going to be the points of intersection between these two parabolas. So as far as those points of intersection are concerned, we would solve the equation that results by setting these two things equal to each other. Adding x squared and adding 6 to both sides will yield 2x squared is equal to 18. Or x squared is 9, giving us that the two bounds will be plus or minus 3. I notice, however, that because both of these functions are even functions and we have this nice y-axis symmetry, the alternative would be we could cover up half of the parabola and simply calculate the area from 0 to 3 and then double that area. I think that's what I'd like to do here. So the area would be, if we had stuck with the original bounds, that would be negative 3 to positive 3 of our top function, 12 minus x squared, minus our bottom function, dx. However, using the symmetry that's present within the problem, we can also call that 2 times the definite integral from 0 to 3 of, let's combine some like terms in here. 12 minus negative 6 will be 12 plus 6, and negative x squared minus x squared will be minus 2x squared. Then, applying the fundamental theorem of calculus, part 2, we find any antiderivative of this. 18 will become 18x. 2x squared will become 2/3 x cubed. And we'll plug in our bounds of 0 and 3 and subtract the result. So 2 times 18 times 3 minus 2/3 times 3 cubed. Simplifying this as much as possible, I am seeing 54 minus 18 times 2. 54 minus 18 is 36. Doubling the 36 gives us 72 for the total area.